You see the marks, and also you decide yourself today, uh, or today, yes. You are supposed to give the, or can be given Friday also, you can give it. If possible, you can give it today so that I can convey this to Soma madam also.
Sir,
Quiz
I'll try to give today, sir.
quiz 4 and quiz 5, है ना? So it will be easier for you because everybody will try to keep the quiz in the same day. So you will be able to avoid it or the overlapping of the quizzes. If you schedule it earlier, it will be better for us, for you also, because we have some other objects, some other paper also, isn't it? So try to give it by today. It will be uh, better for me. Give it today or maybe Friday. You 20, if possible, give it today.
Yes, sir. I'll just try and ask everyone, sir, what day we should keep, and I'll try to save today, sir, or I'll save Friday if it is not possible.
Okay,
And yes,
okay.
sir, we got our marks.
Hmm. And on Friday
Yes,
also, I'll take that extra class because 1 week I'll be absent most of the time. That's why I'm trying to cover it quickly, as quick as possible. Friday, as usual, 10 to 11 and 12 to 1. Friday. Okay.
yes, sir. Yes, sir.
Slide is visible.
Yes, sir. Sir, you're
So,
not audible, sir.
not audible. Now it's okay.
Yes, sir.
Is
Now it's
it
okay.
okay? Okay. Actually connecting the tab. That's why. Anyway, now so last times we are discussing the optical amplifiers. I told you what is the need of optical amplifiers in haptic communications. Uh, it is because if you can increase the repeater spacing, repeater spacing or distance between transmitter and receiver by using a repeaters, right? But if number of repeaters are there, then obviously cost will be very high. And also, if you consider a particular repeater, these functions are to be performed. I told you last times, you need optical to electrical conversion. The next, you need amplifications, and not only that. In electronic domains, you have to do the retiming, pulse shaping, etc. And again, you have to convert electrical to opticals. So these are the things that are to be done in the repeaters. So it is very costlier and also complex, particularly for if you consider the multi-wavelength transmissions in optical fiber, DWDM systems, these things are there, wavelength multiplexing, these are more than one carrier are being transmitted. So it's very much complex phenomena will be there if you consider the more number of repeaters. So instead, uh, but you can have another options that is where there is no need of conversion from optical to electricals. Directly in the optical domains, you can amplify the signals, right? That is done in the optical amplifiers, and it is very much useful not only in point-to-point link but also in networks, multi-access networks. In fact, here you see how it is being done without converting to ऑप्टिकल टू इलेक्ट्रिकल डोमेन्स। इसका आवाज क्यों दे रहा है फैन का? थोड़ा हाँ दिक्कत है ना? हाँ थोड़ी देर के लिए करूँ। सो इसको चला सकती है ये वाला फैन, इसका आवाज नहीं, ये वाला आवाज नहीं करता है शायद, ये वाला फैन। In optical amplifier, how amplification is done here? In that case, whenever actually there will be a pump source. It can be based on semiconductor or optical fiber that we have seen it, where input signal, suppose through the fiber input signal is coming, and because of the pump source in the mediums, electrons will be excited in the higher energy state. And whenever the signal photon that is coming through the fiber input signal, when it strikes the excited electrons in the upper energy state, it will be forced to make a downward transitions, right? And that times photons will be emitted, but that photon energy is the same as the incident photon. So energy, wave vectors, polarizations will be same as the incident photons. But keep in mind, it will not provide the coherent output just like laser. It is not like the laser, but it will provide the amplifications through stimulated emissions. That is the principle of it. I think these things uh, I've shown it. You can see it here. Where here you can see this is a basic principle. Keep in mind here. Some this active medium can be semiconductor 3-5 compound semiconductors, or this one. It can be semiconductors, or it can be optical fiber, like these things. Sort of the case. Because of this pump source, electrons will be excited in the energy state, and whenever the input signal is coming, say it is 50 nanometer, I told you, then it will forced. It will force the. It will compel the excited electrons to make a downward transitions, and in the process, photons will be emitted. That photons will be same as the incident photons. So in the process, amplification will be amplification will provided. You will get the amplifications. You see it here. The signal, much attenuated signal is here, but after these amplifications, you see we are getting amplified output. That is the basic principle of these optical amplifiers. And just see how it can replace the repeaters. There is no need of conversions. You can okay, you can consider the cost, but speed cannot be balanced. You see, speed it will be less if you consider the optical to electrical optical conversions. So if you have all optical systems, then you can have very high speed systems, high speed communication systems, and that is most essential nowadays. Right, and also we have seen it. It is 4 types of optical amplifiers are there. It can be inline amplifiers, where to increase the distance to compensate the attenuations. That is inline amplifiers. Pre-amplifiers to compensate the signal to noise ratio just before the receiver. Before the receiver, signal to noise ratio will be degraded. So to get the moderate value of signal to noise ratio, you have to have these pre-amplifiers. That time it is called pre-amplifier. Pre-amplifiers used to increase the signal to noise ratio at the receiver end. Power amplifier, that is to increase the power. See, once you have the laser source or LED source, whatever the case, the power is fixed. You cannot increase the power, but if you increase the power, then more distance and other things can be considered. But here, you see, using these optical amplifiers, you can increase the transmitted power, right? I mean, more distance can be covered. More distance can be considered for communication systems. So another applications I told you, there is a booster amplifier. Whenever many stations are interconnected, that time splitting loss will be severe. So that splitting loss can be compensated just before the splitter if you use these optical amplifiers, right? So that is a booster amplifiers. So you can have 4 types of amplifiers, and you see it can be two types. I told you semiconductor optical amplifiers or doped fiber amplifiers. In semiconductor optical amplifiers, 3-5 compound semiconductor is used, very similar to laser structures. I told you, you see, these are laser structures, the 3 layers are there. You see, this is a confinement layer, this is another confinement layer, in between there is a active regions. Right. So in the active regions, actually stimulation emission takes place. This is the incident photons. And after stimulations, you see, you'll get the amplified signals. Right. So that is the structure of this configuration of the semiconductor optical amplifier. Here, the advantage is the in semiconductor optical amplifier, rapid carrier response is here. You see, rapid gain response is here. Rapid gain response is here. It is around 1 picosecond, or there are 1 picosecond. But again, this can be a disadvantage in the process that gain can fluctuate, and so crosstalk may appear, particularly if you consider the multi-wavelength operations, right? So crosstalk will be a disadvantage for this the rapid response of the semiconductor optical SOA. So these problems can be overcome if you consider the fiber-based amplifier, doped fiber amplifier, where doping can be rare earth elements. You see there the rare earth elements. Rare earth elements means erbiums, ytterbiums, neodymiums, praseodymiums, etc. एक ही इसी है, एक ही ऐसी कुछ करना, हाँ, दो ऐसे नहीं है, हाँ ठीक है, दो ऐसे करने से फिर वो तो वो बंद हो जाएगा फिर, हाँ, लोड उतना लोड नहीं दिया, हाँ, तो so gain can fluctuate. I mean here, so this can be overcome in doped fiber amplifier. Doping can be rare earth elements like erbiums, ytterbium, praseodymiums, neodymiums, etc. Out of these, generally erbium and ytterbiums, particularly erbium doped fiber amplifier EDFA, that is used in the 1550 nanometers. Sometimes ytterbium is used to enhance the performance, right? EDFA is most widely used rare earth element for the optical amplifiers. But for 39 nanometers, it is not useful. 39 nanometers, you need fluoride-based fibers. Earlier one is the silica fibers. And in that case, doping elements will be neodymiums and praseodymiums. Neodymiums and praseodymiums, ND and PR, praseodymiums. They are the doping elements. And this is useful for these 39 nanometers, right? 39 nanometer, you need these elements, and the glass host materials will be the fluoride-based fiber, right? And if you see whether it is fluoride-based fiber or silica fibers, in doped fiber amplifiers, you see you can have very low coupling loss, because it is fiber, it is not the semiconducting materials, it is fiber. The dimension is compatible with the incoming fibers, right? This EDFA can be 10 to 20 meters in length, 10 to 30 meters in length. Of course, you can increase the length, but gain will decrease. That just last time we discussed, today I'll also discuss in details. And also it will have low dependence on polarizations, and there'll be no crosstalk here in doped fiber amplifiers, and also no intermodulation distortions. Those are present in case of the semiconductor SOA, semiconductor optical amplifiers, right? So the doped fiber amplifier will have these advantages, right? And if you see the semiconductor amplifiers, again, it can be of two types. It can be Fabry-Perot type amplifiers, or it can be traveling wave amplifiers. The Fabry-Perot amplifiers, their configuration is very similar to laser structures. Here also similar to laser structure, but here there can be multiple reflections. In APA, Fabry-Perot types, multiple reflections are there. But in case of traveling wave amplifiers, only there will be a single pass. There will be no reflections. single pass gain can be achieved only through single pass, not through multiple reflections. And if you have this, I mean, that is possible if you have anti-reflection coating. And you see what will be the advantage of these traveling wave amplifiers? You can have large optical bandwidth. You'll have high saturation power. And third one is also important: low polarization sensitivity. No polarization sensitivity. Sometimes polarization also will deteriorate the bandwidth or the data rate. So that will be insensitive to polarizations and traveling wave amplifiers. Right. So these are the advantages of traveling wave amplifiers. Right. So it can be two types. Semiconductor optical amplifiers. Their architecture can be two types. One is the Fabry-Pérot types, Fabry-Pérot type amplifiers. Another is traveling wave type amplifiers. Right. So and if you see in general their gain factors, how can you calculate this? How can you estimate the gain factor? You have to consider for that. You have to consider the rate equations. Rate equations means rate of change of carrier density. If you just consider, then it is the pumping rate, because you are using some pump source. So pumping rate that will make the transitions from ground level to higher energy levels. And after that, when the signal photon strikes the systems, then there will be stimulated emissions. Also, there can be spontaneous emissions. So that is the stimulated emissions, and they are the spontaneous emissions. Also, there can be the carrier recombinations. Right? So the number includes this lifetime includes the spontaneous transmission as well as carrier recombinations. Right. And if you see this pumping rate RP, it depends upon the semiconductor optical amplifiers. It depends upon this the current density, the injection current, right? So J by QD, that is pumping rate, the number of carriers injected, that is the pumping rate, current turns. And RST, that depends upon these several factors. That is the gamma, the confinement factors. We have seen this confinement in the calculations. So confinement factors, the gain constant, group velocity, the velocity, and n minus n threshold, that is the threshold current density, and NPH also. It depends upon the intensity present. I mean, photon intensity present. See, stimulated emission means it will be stimulated by some photons, external photons. So that photons actually the NPH, photons density. So and all the factors can be considered as G. Constant factors can be replaced by G. So this is G times BG into NPH. Right, that G actually represents the overall gain per unit length. And what is NPH? This photon density, that is the input signal power divided by this photon energy, that will give you the number of photons per unit volumes. That is photons per unit volume. If Vg is a good velocity, that means in 1 second, that is Vg centimeter. If you just per second, that will be the Vg centimeter, right? And that is the length into width into thickness, that will give the volumes. So that is the photons per unit volumes, right? That is NPH. This is the most important relation. Sometimes it is given some, it asks to some silly questions are there based on this photon density and the estimated transition rate. And so in the steady state, the rate equations we have seen it. So in the steady state, this dNt upon dt will be 0. So if you just solve it, you'll get the gain factors. This G will be G0 by 1 plus NPH by NPH saturations. This G0 is the small signal gains. Again, when there is no signal input, that is G0 is given by this gamma A tau R. J by QD minus n threshold by tau R. So that is the G0, the gain in absence of signal input. right? And NPH saturation, it is the factors used by this one, 1 by gamma times VGA times tau R. So this is replaced by this factor NPH saturations. So we are getting these equations. Gain factor G, that is equal to G0 by 1 plus NPH by NPH saturations, right? And that is the actually internal gains. These are the internal gains. Now overall gain, if you see, then it is input by output by input. That is the gain that you know it for any device amplification, any amplifiers. Gain, that is that just now what we have discussed, that internal gains, mediums. In the gain factor depends upon these parameters: photon density, confinement factor, group velocity, etc., tau r, etc. Those factors are involved. But if you see in a device which is provides the amplifications, so the gain factor or amplification will be output by input. You see, output by input. So there is PS out by PS input. Single pass gain. And there is a gain, and for single pass gain, so one length L will be considered, and also you see this is the gain factor, this confinement factor gamma, and this alpha, the absorption will be there. So the G can be expressed GM, the material gain. Just now what I discussed, the G, that is actually GMs or G. Metal gains, simply to distinguish this gain with this gain. So GM is used instead of G small g. That small g actually this one, this small g, that is the metal gains. So now it is replaced by this GM, small gm. But not only the gain, some absorption scattering always will be there. So that factor is included here. So it is gamma times constant factor times GM minus alpha bar times L. Single pass, only one L is considered. So that is exponential GZ times L. Right. So that is the GZ is the overall gains. Right. So it seems gain will increase the length of the amplifiers. I mean, if the if the length of the amplifier not 8 it is actually semiconductor optical amplifier. So if the length of the semiconductor material increases, the gain will increase exponentially, but not like that. After a certain times, you see, certain instant, there will be no excited carriers in the upper energy states. So the gain will, even if you increase the length, there will be no increase in the gain. Gain will fall, right? That will see it graphically. I'll just show it. So NPH we have seen last time. So these ones, G is these ones. So and G, so GZ, G will be a function of Z. We just consider Z at a certain distance Z. GZ will be these ones. Can be expressed from the previous relations, and for a certain incremental DZ in that with semiconducting optical amplifier, certain increment DZ, then power will increase. The DP, that will be GZ, then PSZ times DZ. And if you just consider DP by PSDZ, that will be GZ. GZ is equal to these ones. So this will be these ones. Just rearranging the relations. So for a small incremental distance, what will be the power? There is a power. Now, by integrating these things, we can have the total Z0 to L. You can have the total power. So that is 0 to L's. So Pn into P output of these ones. And ultimately, the gain, this G will be obtained by these ones. That is the gain. And you see here, I told you, you see, even if you increase the length or input signal power increases, the gain will not increase. So after a certain times, you see the gain will fall. That is because even if you increase the input signal power, gain will fall because there will be no excited electrons in the upper energy state. So if again it will be populated, then you'll get the gains. But since input signal power increases, so there'll be no carriers available in the upper energy state. So that's why gain will fall. Right. So that is the reason of this, the nature of this card. Right. Okay, that is the semiconductor optical amplifier. Now, semiconductor optical amplifier advantage is this. Again, you see, I told you here rapid gain response is there. Rapid gain response is there, but drawback is the crosstalk and intermodulation distortion. Those things are there. So those are those problems are avoided in case of EDFA. In case of erbium amplifier amplifiers, it is 10 to 30 meters in length, and doping generally 1,000 parts per million. Doping is used. Erbium ions that is doped within the silica fibers. This erbium ER. Sometimes ytterbium is used to increase the performance, but that is combination is used for 1550 to 1550. It can be enhanced to up to 1560 to 1610s also. Up to 1600 can be extended using the ytterbiums. Right. Just a minute. Extended to 1560, but still it can be increased to 16 nanometers if you consider the Raman fiber amplifier, using a Raman fiber amplifiers. Raman fiber amplifier, you can have still can be increased, range can be increased. But in the 1300 nanometer regions, you have to consider the fluoride glass I told you. At that time, doping elements will be either neodymiums or praseodymiums, right? The PR, right? So they are the rare earth elements used for erbium doped fiber amplifiers, right? Same thing is mentioned here. Yes. So here it is shown the same thing, rare earth elements, fiber, silica, glass fibers, silica dopants, dopants are erbiums, or sometimes ytterbiums are added to increase the performance. I told you 1530, 1560, and in case of still can be increased more if you use the Raman fiber amplifier. And it is based on this erbium doped fibers here. Here is based on the ledging principle, and here it is actually two-level ledgers. Ledgers can be 3 levels, 4 levels, or 2-level ledgers. Semiconductor used, say semiconductor is 2 levels, valence band, conduction band, right? 3 levels ledger. They are the different types of ledgers. In the 3-level ledgers, there is a palm band, next upper ledger level, lower ledger level. These things are there, right? So there are different types of ledgers are there. So erbium doped fiber amplifier also, it is very similar to these ledging principles, right? No, it is 3-level ledgers. It is not for 2 levels. 2 levels it is in case of semiconductor optical amplifiers, SOA, right? That is principle behind it. 2-level semiconductor conduction band, valence band, but in a 2-level system easier. But here it is EDFA. It is based on 3-level systems. 3-level system, that is because you see these amplification mechanisms in erbium ions. These erbium ions. So here you can see 3 levels. There is a ground state. This is the metastable state, and this is the palm band. Actually, 3 levels, 4 levels. How it is being distinguished? 2 levels, so it is just 2-level conduction band, valence band, and conduction band. 2-level systems. Valence band, conduction band. 3-level systems, very similar to this figure. There will be a palm band. Next, there will be a upper ledger levels, and next lower ledger levels. Upper ledger levels, lower ledger levels. Here, lower ledger level is the ground state. This is the ground state, right? And this is the palm band. Palm band. This is the upper ledger levels. This ones. In case of 4-level ledgers, this lower ledger level, it is not the ground state. It is slightly above the ground state. You can see it here. So there are 4 levels. So these ones, you can see these ones. So there are 4 levels: ground levels, palm levels, upper ledger levels, lower ledger levels. This is actually converted to 3 levels when these 4 and 1 and 4 they merge together. Then it is 3 level systems. So this is basically a 3 level systems at PAM. Here you see there is a ground state. This is a palm band, and next there is upper ledger levels, or you can say metastable state, and these ones, right? So here actually, if you see, palm source is used, and here palm energy greater than palm energy should be more than the signal energy, signal photon energy. So pump energy, HC, if it is pump energy, say H nu P, if H nu P is greater than this H nu S, signal energy, signal photon energy, then it's C by lambda, right? That means lambda will be inversely proportional, so lambda will be less. Lambda less, lambda P will be less compared to this Hc by lambda S, signal photons. Signal photon wavelengths, so lambda P less than the lambda S. So then only photon energy, a pump photon energy will be more. So that's why now with this principle, if you just see this principle, signal photon is generally 1550 nanometers. So the pump photons, it will be this one. Pump photons should be less than this 1550. Generally, 2 wavelengths are used, that is 980 nanometers, and that is 1480 nanometers. These 2 wavelengths are widely used for the pump photons, pumping systems. I have shown you the basic principle. The pumping energy, pumping source is equal. So here, if you see the transitions, several transitions are there. You can see it here. Initially, when the pump source is used, I'll show the architecture. Then you see when the pump energy is used, then electrons will be excited in the pump energy levels, and you see the pump energy to the pump band to the ground state. The band gap, it is 1.27 electron volt, and here it is in this case top of the it is not a slightly different way. Top of the ground state to the bottom of the metastable state, it is 0.77 electron volt. It's not like these ones. It is these ones from here to here. Top of the top of the ground state. You see, these are not sharp levels. Some band is here. So top of the ground state and the bottom of the metastable. Metastable means the life state which are having larger lifetimes. So this times this it is 0.77 5 electron volt, right? That is the band gap between these two, right? And of course, that depends upon the wavelength also. Here it is around 16 nanometer. If it is 1527, then it will be 0.84, 0.814 electron volt, right? The gap between the these two bands, right? So that is most important. Then only you can have the same energy, same photons as the incident photons, 1550. So if you see the process, because of these pump transitions, pump photons, pump 980 nanometers. There are 2 pump wavelengths actually, 980 or it can be 1480. If you use 980, then it will be excited, electrons will be excited in the pump band, and next there will be a fast decay, that is non-radiative decay. There will be decay, and it will be the top of the metastable states. And after that, there will be decay, soft decay will be there into lower state. That is the fourth transitions. So that is 1, 2. Also, 3 times this third transition is sometimes 1480 nanometer is, but at a times 980 or 1480 both is used. This here it is diagram. It is shown in the case that if 1480 wavelength is used, then there is pump band will not be there. Directly, electrons can be excited to the metastable states. But this top to bottom transitions will be there. After that, so the lower of the metastable states will be highly populated. Next, when the signal photon strikes the systems, then there can be stimulated emissions. You see there is a stimulated emission, which is the same as the incident photons between 50 nanometers. Of course, you cannot avoid this fifth transition, that is a spontaneous transition. This always will be there. Whether stimulated agency is there or not, spontaneous emissions always will be there. That is at 50 nanometers, right? But in the process, you cannot avoid the stimulated absorptions. Some absorption will be there at the same wavelengths between 50 nanometers. That is these ones, right? So that is the amplification mechanisms for the EDFA. So here it is, of course, it is not some signal photons will strike. Signal photons, then stimulation, it is not a natural process. So whenever the signal photons, that is at 1550 nanometers, I told you, signal photons will strike the systems, then excited electrons will be forced to make a downward transitions, right? And in the process, the photons will be emitted, same photons as the incident photons will be emitted, that is 1550 nanometers. So that is the principle of it. So the different transitions are there. So that is the pump transitions, that is a fast decay, that is a short decay times, so decay will be there, that is the fourth transitions. Third transitions, if 980 is not used, then this one directly can excite this one. Next, there will be spontaneous transitions, there can be stimulated transitions. Also, there can be stimulated absorptions, right, at these wavelengths. So this is the amplification mechanisms for EDFA. Next, if you see architectures, you see actual architectures, what will be the configurations? You see architectural configuration. You see here, actually, this is the there are 3 architectures are there. One is for called co-directional pumping. Another is counter directional pumping, another is dual pumping. Co-directional pumping, you see both pump and the signal photon propagate in the same directions. If you see these architectures, you see that is actually this is the EDFA, the short fiber length. It can be 10 meter to 30 meter in length, right? And here wavelength, one side there will be wavelength selective coupler is here. Wavelength selective coupler is here, coupler to couple the pump source as well as a signal source, right? And here amplification will be made, and after that there will be opto isolator is there to block the reflection or of light from the to enter into the device, entering into this one. Reflection light it will block, right? And next taper coupler is here on both sides. This is one, another one taper coupler. So these taper couplers are used to check the ratio, to check the amplifications, to compare the incoming signal and the amplified signals. And the ratio can be 99:1 or can be 95:1, right? In this ratio. Right. These ones. Incoming signal to the amplified signals. A small portion of signal is taken. So you see 99:1, 95:1. To compare the incoming signals with the amplified output. And these 2 isolators are there to block the reflection of signals into the entering into the device. Right. The same principle is there in counter directional pumping. You see it here. Here, same thing, all the things are there, but here signal photon is propagating in these directions, but pump photon is propagating in the opposite directions, counter directional pumping. This is a pump photons. This is the signal photons. Signal photons. You can see it here. So it propagates in these directions, and pump photon propagates in these directions. Counter directional pumpings. Other things are same: two couplers, two oscillators, one wavelength selective couplers is here in output. So then, what are the characteristics of this co-directional pumping? It is very much useful towards noise suppressions. So noise performance, if your noise suppression is here, then co-directional pumping is very useful. But whenever high gain is required, that times counter-directional pumping is used. Of course, there is another architecture is here, that is dual pumping. It's a dual pumping. This one is a dual pumping. Here, both co-directional pumping and counter-directional pumping is used. Of course, there you see the previous diagrams, and in this diagram, the difference is there are two wavelength selective couplers are there. You see both sides to couple the pump source into the amplifier. So other things are same: step couplers, opto-isolators, cup-type coupler. These things are there. So dual pumping, both the advantages you can have it, which are obtained in case of co-directional pumping and counter-directional. So keep in mind, co-directional pumping is full for noise performance, and counter-directional performance is for the gain. High whenever you require high gains. So both the things can be obtained. You can, if you consider the dual pumping. Of course, some extra components should be there on the WSC, wavelength selective couplers is here. And if you see the power conversions, just 1 minute. Okay, some more things are there. Okay, quantum conversion efficiency. Okay, now power conversion efficiency. So that is another important aspect. So it is actually power. Let's say amplifications means small to the high, but from here you are getting the energy. And say for conversion amplifier, you also same thing. Generally, it is obtained from the applied voltage, right? Here also, the energy actually it is obtained from the pump source, right? So the maximum gain depends on the pump. It cannot be it cannot exceed the pump energy, right? But also we have seen it. The pump photons always it is the wavelength of pump photon is always less than the lambda s, because pump energy should be more, and so hc by lambda inverse, so lambda p always it is less than lambda s. And if you see the conservation principle of energy, so output power, signal output power will be input power plus the pump power with the ratio lambda p by lambda s. This can be obtained. This can be through the energy conservation principles, right? Lambda p by lambda s into pp pump power input, and this is a signal power input. That is the signal power output, right? And in the process, always signal input should be less than pump power input, right? And if you see. Here, one thing is important. Sometimes this amplifier can act as a window also. Okay, with that we'll see it. Okay, next time we'll see it. To this much till power conversion efficiency. Okay, next time we'll see it. So if you have any questions regarding this optical amplifier, you can ask anybody if you have any questions. किसी का question है? Anybody if you have any doubt?
No, sir. Yes, sir.
अच्छा, also, but then have you decided the quiz 4 and quiz 5?
Sir, actually, I have discussed the class, sir. We'll inform you in next class, sir.
Okay, then Friday 10 to 11 class will be there. Another class will 12 to 1. Friday.
Yes,
So
sir.
Friday you just confirm me. Okay. Then I'll
Yes, sir.
convey these things to convey these things to section B.
Yes, sir.
You have to decide earlier, right? I have uploaded the lecture also. You can see it.
Yes, sir. Thank you, sir.
Okay, then